going over the physics free fall FIP quiz. The first one is a kind of problem. The first one is a kind of problem that really rewards careful reading, and I wouldn't throw a curveball like this at you on a test, but I don't feel bad at all about throwing it to you on a FIP, because you have to read carefully and you have to think about the situation. Physics is all word problems, it's all applied. So if you are climbing up the cliff face with a banana in your teeth, which is kind of a weird thing to do, but you know, hey, it's physics, and you are moving, or in your hand or whatever, and you are moving upward at a velocity of 1.3 meters per second, how fast is the banana moving and in what direction? The banana is moving at the same velocity you are. The banana is moving upward at 1.3 meters per second until the moment you drop it. So the banana's initial velocity is not zero. And you have to think about, and that's where it becomes even more essential in the next chapter, but it really helps in this chapter, draw the picture. Especially for some reason on the free fall problems, the y-axis problems, to understand where in the motion we're talking about, it really helps. So drawing that banana is moving upwards. Oh, okay, so my VI is actually 1.3 meters per second. Acceleration, because we are on Earth, is always, negative 9.81 meters per second squared. And what we want to know is how fast is the banana moving at 2.5 seconds. So this one was an easy one in that you didn't have to do any rearrangement. Let's talk about what you get points for on a test. If you do get frustrated with a problem on a test, list your variables. Draw a picture. I give you a point for each of those things. So out of 10, if you get nothing other than your picture and your variables, you're going to get -8. If you can pick the correct equation, that gets you another point. If you can rearrange it correctly, that typically gives you another point. So for this, we're connecting VIA, delta T, and VF. Easiest bet is VF equals VI plus A delta T. And that's the one that always makes intuitive sense to me. How fast you end up going is how fast you started out going plus how fast you're accelerating, the amount of time you've been accelerating. So that's one that actually I think is logically sensible. Some of them aren't because they're so far derived from the original motion stuff. But this one's pretty straightforward. So we plug it in, and the most common error was, of course, people forgot to factor in that 1.3 upward, that the banana was not stopped when it started moving. So we end up with a VF of negative 23 meters per second. And that was one where I think most of you, had you considered the motion of the banana initially, would have gotten it. If that's the only thing you missed, don't beat yourself up. Don't beat yourself up, period, because, hey, it's just a physics test. You have your friend there, and the point where their hand is 8.75 meters up. And that's also crazy tall stands. This is like the YSU stands. This is not our stands. We'll actually get rid of that for now. So you're throwing this thing, and it is starting off 1.5 meters above the ground. It's going to travel up some distance. We don't know how high. And if your friend doesn't catch it, it's going to fall back to Earth. So we have VI, and you really winged this thing. 15.9 meters per second is no joke. That's a pretty good throw. You have a VF at top of flight. VF at top of flight is always what? Zero. 0 meters per second. And we have acceleration, of course, because we're on Earth within the confines of the atmosphere. What we'd like to know is how high does this thing rise before it stops and turns around? So the easiest expression to use is VF squared equals VI squared plus 2A delta Y. We are, of course, rearranging to solve for delta Y. The things that I list, I try to model good problem-solving strategy for you. draw the picture, list the variables, write the base equation. Just as a matter of habit, I typically circle what I'm solving for if I have to rearrange or underline it. It's a nice visual cue for me. I noticed a few people still kind of struggling with rearrangement, so we can do practices, we can do tutorials. Tonight's my tutoring by appointment night, so if you need help, come get it. Where were we? So you've circled what you're rearranging for. From here, if you made mistakes, for most people they were probably algebraic. VF squared minus VI squared divided by 2A gives you delta Y. When you plug that in, what you get as a raw answer is 12.8853, etc. meters for delta Y. So, the simple question is, will the keys reach your friend? And the answer is yes. But it says, in other words, what is the maximum height? Well, this is the change in its position. And again, careful reading. You have to add the fact that it started 1.5 meters off the ground. So if the only thing you did on this problem was you put in that as a final answer, I probably underlined max height on there. So max height, and you can put in this justification. Let me shrink that. Let me shrink all of this. Yep. So max height equals delta Y plus 1.5 meters. Max height, and your final answer is 14.4 meters. Okay. So that is the maximum height. Question? Okay, so we know that the keys certainly sail up over your friend. Your friend is capable of catching them, but do they? That's the other question. So from the beginning, if the keys don't reach them, I'm sorry, it's not keys this time, it's a golf ball, or they can't catch them, how long would they be in the air before hitting the ground? And again, drawing the picture really helps. So here we're talking about their total flight path. So all the way up to the top, all the way crashing back down to the earth. Always, if you can, avoid using the thing that you just calculated. And also on this, I had, for the people who did solve it correctly, I think I had a couple different solve methods. So some of them fairly circuitous. Remember, for every single physics problem we do, there are probably 6 ways to solve it. 4 of those will probably give you an answer, and 3 of those are probably the correct answer. There's typically one way that's elegant, which means it's straightforward, it's streamlined, it's easy. And like I said, I used to give a bonus point if you found a more elegant method than me. I haven't had to do that in a few years because, for the most part, I've gotten down to the streamlined method. But my first year, man, my solves were pretty circuitous. They went around the barn. You just want to avoid introducing possibilities for error. So what do we know here? Well, we know VI, 15.9 meters per second. We know acceleration, negative 9.81 meters per second squared. And we know delta Y. What is delta Y? No. Negative 1.5. Because it started off 1.5. Like I said, this is just like Maria and the Apple, Part B. This thing did not start off at ground level. It started off 1.5 meters above the ground. So if it comes crashing back to Earth, its delta Y is negative 1.50 meters. Now, what we'd like is delta T. The only equation we have that connects all of those things requires a quadratic solve unless VI is 0. So if we did delta Y equals VI delta T plus 1/2 A delta T squared, if VI is 0 and that goes away, that's fine. But if VI is not 0, then this would require a quadratic solve. So since I hate the quadratic equation so much, one of my personal growth goals, I will get better, there has to be a workaround. So we have this nice little equation. We have VF equals VI plus A delta T, which would give us delta t, except we don't have VF. But we have everything that we need to build an expression for VF. And I'm kind of focusing on these problems because they're great preparation for what comes next. In the next chapter, we pretty much do substitutions every single time. So it's a good thing to just sort of gird yourself for, get ready. We have this lovely little equation, VF squared equals VI squared plus 2A delta y. And VI, A, and delta y are all things we have. So we can create an expression for VF, and that's really easy. VF is just the square root of VI squared plus 2A delta y. And then we can insert this expression in for VF. You would be wise to do that after you've rearranged it because it's a little bit more nightmarish if you do it beforehand. So I would rearrange this for delta t, VF minus VI divided by A equals delta t. So then we have this expression that we can neatly pop in for VF. We're not using a calculated number. We don't have the risk of forgetting what we're doing and rounding it before we put it in. So what that looks like, let's move and shrink, is square root of VI squared plus 2A delta y. And if you need to put that in parentheses for yourself so you don't forget where that radical ends, do it. I sometimes do that to just kind of keep my work neater for me so I don't screw up. Minus VI divided by A equals delta t. The question always comes up here, well, why can't I just calculate VF and then plug it in? That's in essence what you're doing. The reason to get used to doing the substitution, as I said, is that in the next chapter, in the next 2 chapters, it is all substitution. It is all expression building and substitution. In chapter 4, that's about all we do, is expression building upon expression building. So I really, it's a skill that I want you to build now. This is not the only way to solve this problem. You can compute the time it takes to go up. You can then compute the time it takes to go down because you know how high it went and you've got an initial velocity. You can add those two together. You can certainly do that. And I have. My first year teaching physics, that's how I would have solved it. Because I couldn't yet see the elegant path. But whenever possible, strive for elegance. Strive for the simplest solution. So what we get out of this as a raw answer is 3.33333. Oh, here's the catch. Here's the catch. Always remember that in that kind of substitution, when you're taking a square root, that's positive or negative. Well, what you have to do as the architect of the problem is think to yourself, what am I substituting that in for? Well, that is the VF. This thing is coming back down towards the Earth. Will VF be negative or positive? Negative. If you put that in as a positive number, you get a completely different magnitude. So this ends up being, what, 16.8 meters per second? Yeah, so the number that we get for this is 16.8 meters per second. We have to mentally go, oh, that's a final velocity of something crashing towards the Earth. That's going to be negative because that is plus or minus. So it ends up being negative 16.8 minus 15.9 meters per second divided by negative 9.81 meters per second squared. Now, of course, that gives you a negative number divided by a negative number, which gives you a positive. You want positives for time. The magnitude of the number you get is radically different if that 16.8 is not negative. And one of your first clues in doing a test would be, hey, I got a negative number for time. That seems strange. There are some problems where it's just like, oh, we can flip the sign. But a lot of times on the y-axis problems, if you're showing up with a negative number for time, you've done something else and you need to go back and re-examine. And the critical things that typically trip people up are, oh, I have a final velocity here that I put in as a positive, or I have a displacement that I put in as just the magnitude, but it was a negative displacement. Those are the kind of things that typically throw you off. So the raw number that we get for this is 3.3 repeating. With our 3 sig figs, we have 3.3 seconds. So our final answer is 3.33 rather, seconds is delta t. Questions, comments, concerns? So you find yourself on some alien world, and one that we'll assume is safe for you. You drop something down a cliff. We have a cliff. I'm going to generalize that object to just a round thing. And what we're told is that it hits the bottom in 4.75 seconds. So we have a delta y. And again, this is a falling object. The delta y has to be negative. So we have a negative 58.5 meters. We have a delta t of 4.75 seconds, because you didn't drop your watch. We have a vi of 0, because in this case, it was still. It didn't have any y. It doesn't say you threw it. It doesn't say you tossed it up. What we want to know is what is acceleration on this planet. So we can use what is honestly, and I don't know why, but a kinematics equation that just makes me happy. Delta y equals vi delta t plus 1/2 a delta t squared. We are, of course, solving for acceleration. So to rearrange that, well, the first thing you can do, because vi is 0, we know that's going to go away. And you're welcome to make that disappear. And then delta y equals 1/2 a delta t squared. 2 delta y divided by a square root equals, oh, geez. What did I just do? I just solved for delta t because I'm accustomed to doing that. Sorry. Okay. 2 delta y divided by delta t squared equals a. So what we get for a raw answer is negative 5.1855, etc. meters per second squared equals a. So we get negative 5.19 meters per second squared is equal to the acceleration on this planet. Another good add-on to a problem like that would be, what fraction of Earth's gravity is in effect on this planet. So it's going to be about 2/3. Yeah. So you could say, and I didn't ask this, I'm just thinking mentally, and I probably won't even ask it on a test, but so if we took that negative 5.19 divided by negative 9.81, so it's got about half Earth's gravity. It's roughly half Earth's gravity. So we would assume this is a planet that's roughly half as massive. Questions, comments, concerns? Okay. We'll just work then.